In lecture 12, we're going to be talking about the endocrine system, which basically is a system that involves the secretion of various hormones, and often these hormones are going to be responsible for maintaining some kind of homeostasis. Now, you already learned quite a bit of hormones in previous lectures. We've learned about ADH, we've learned about FSH, LH, estrogen. So you will see some of these hormones coming back again in this lecture, and you will see how some other hormones will share similar themes in terms of negative feedback control and positive feedback controls. So this slide shows you all the endocrine glands, or the major ones, that are found in the human bodies. We will be labeling this diagram in the course pack at the end of the lectures, and we will be writing out all the hormones that are coming out from these glands. So for now, just take a look at the picture and kind of see what kind of organs are there, and we'll revisit it at the end of the So first, we're going to begin by talking about the interaction between the hypothalamus and the pituitary gland. As you remember, the hypothalamus is what we call the master gland in the body because it regulates the function and the secretions of many other organs. Closely associated with the hypothalamus is the pituitary gland, which is going to be located beneath the hypothalamus. In the nervous system, we've already learned that the hypothalamus regulates internal environment, or more correctly, homeostasis, the internal balance of various things. For example, through the autonomic nervous system, the hypothalamus will help you regulate things like heartbeat, body temperatures. You might remember when you have a fever, it is the hypothalamus that causes the temperature to rise. And in the urinary system, you learn that the hypothalamus makes a hormone called ADH, which helps you regulate water balance. And it is also the hypothalamus that causes you to have a thirsty sensation when you are dehydrated. So, as we mentioned earlier, the hypothalamus also controls the secretion of the pituitary gland. Now, the pituitary gland also has a different name, the hypophysis, but for this course, we're not going to worry about it. So you can just kind of ignore that for the time being. I mean, it's good to recognize the word, but we won't be using it in the course. The pituitary gland is connected to the hypothalamus through a stalk-like structure, and we'll be looking more closely into the stalk on the coming slides. The pituitary is also separated into the posterior pituitary as well as the anterior pituitary. And again, they have different names, and we don't have to worry about them for this course. In general, posterior pituitary gland it stores hormones from the hypothalamus, and these hormones are made in the hypothalamus, but they will be temporarily stored in the posterior pituitary gland until they are ready for release. On the other hand, the anterior pituitary gland, they will make their own hormone, make own hormones. And in fact, we are going to be looking at 6 different hormones that are produced at the anterior pituitary gland. This is a picture to remind you where the hypothalamus is in relation to the anterior and the posterior pituitary gland. They are structurally connected because, as you will see in the coming slides, that there are neurons in the hypothalamus that would physically extend their axons into the posterior pituitary gland. All right, so in that respect, they are structurally connected, they're physically connected, and they are also functionally connected. So there are neurons that would start at the hypothalamus, but instead of going all the way into the anterior pituitary gland, they would kind of end in this stalk region over here. So this part right here is what we call the stalk region. And you can see these neurons, they start in the hypothalamus and then they will end in the stalk region. And what they do is they will secrete different types of hormones that would then exert their effect on the anterior pituitary gland. So rather than physically connecting the two parts, they are only functionally connected. In other words, the hypothalamus will influence the secretion of the anterior pituitary gland through a set of hormones. You can see the pituitary gland here is protected by this bony structure. And if you remember from the skeletal system, that bone is actually the sphenoid bone. Now, it is important to understand that the anterior pituitary gland is not always shown on the left or always shown on the right. It all depends on which side your head is looking at. So in this particular diagram, the anterior pituitary gland is over here on the right. On the previous slide, it was on the other side. But doesn't matter. What's important is to take a look at this drawing. And this is sort of what I was trying to show you on the previous diagram. In the hypothalamus, you can see there are two groups of neurons. Okay, we got the green ones here, and we have the yellow ones here. The green ones are the ones that will physically extend their axons into the posterior pituitary gland. And there are two hormones, as you will see, that are produced in the hypothalamus, which are then packaged into vesicles, and these vesicles will transport them and store them in the posterior pituitary gland. On the other hand, we have these yellow neurons, and you can see their axons end right here. So rather than going through to the AP, they would only end at the stalk region. So this lists all the hormones that you get from both glands. You can't really see this see them clearly on this slide, but this diagram is taken from your textbook, so you can look it up and study a little bit more. But don't worry about it too much for now. Okay, we are going to go into much more details into these hormones as we progress through the lecture. So let's talk about the posterior pituitary gland first. Right? There are two hormones that are made in the hypothalamus, right? But they are stored in the posterior pituitary gland. You've learned ADH previously, right? And you know that it acts on the distal tubule, collecting duct, to help the body conserve water. There's a spelling mistake here, sorry. To help the body to conserve water, right? Particularly important when you are dehydrated. There's a second hormone that is made in the hypothalamus and stored in the posterior pituitary gland, and that one is oxytocin. Oxytocin is more important in females than it is in males. There are two main functions for oxytocin. The first one is to create a contraction of the uterus, and you need to contract the uterus when you're giving birth, okay? And the other function of oxytocin is to let the milk let down, which basically means let the milk come out when you are feeding the baby, right? So both of these are obviously very important for mothers. And one other point to think about is that oxytocin actually uses what we call positive feedback. Now, this is not the first time we mentioned about positive feedback, right? If you think back about the reproductive system, estrogen is another example of positive feedbacks, right? Most of the hormones that we learn uses negative feedback, but estrogen and oxytocins are examples of positive feedback, where the hormone is going to exaggerate the initial stimulus that causes the hormones to be released in the first place. So let's think about why this makes sense for oxytocin. So let's say you are going into labor, which means the baby is ready to come out. So the uterus is going to have a little bit of contraction. That contraction actually will go back to the hypothalamus, and it will trigger more oxytocin to be released from the posterior pituitary. And it makes perfect sense because once you have a little bit of a contraction, you actually want to have more contractions until the baby comes out. So in that way, it's exaggerating the effect. You get more of the same thing, right? Until you've accomplished the task. In this case, letting the baby come out. Same thing when you're trying to feed your baby, right? If your baby is, you're nursing your baby and the baby is suckling, you don't want the milk to stop coming out, right? You want more milk to come out, right? Until you're finished feeding the baby. So that's oxytocin. Now, just a side note, it turns out you don't actually need the baby to be suckling sometimes for the milk to come out. Some nursing mothers would tell you just by hearing their baby crying, right? Just the sound of their baby crying is enough to trigger the letdown of the milk. Okay, so that's oxytocin, ADH. They are both hormones made in the hypothalamus, but then stored and released from the posterior pituitary gland. This is a diagram that goes through the steps of how hormones are made in the hypothalamus and how they're transported down to the PP, right? And once again, the position has changed, right? Over here, we have the posterior pituitary gland on the right here. Right? So in the stalk region, you can see there's a bundle of axons that are coming down from the hypothalamus, and all of these are going to be going to the posterior pituitary gland. So in that respect, hypothalamus is structurally, physically connected to the posterior pituitary gland. All right. So if you want to think about this as an analogy, right? This is like your DVD player or something, and this is kind of like your TV, and you are connecting them through a physical cable. Next, we will see that rather than having a physical connection between the hypothalamus and the anterior pituitary gland, the connection is more of a functional connection, right? It's more like Wi-Fi connection, if you want, between your cell phone and your TV. Now, it uses a system called the portal system, right? What is a portal system? It's basically two networks of capillaries that are very close to each other, and then they are connected by blood vessels, right? Usually a vein in most cases. And this is not the first time you learn about the portal system. If you think back in the urinary system, right, there was actually a portal system for the nephrons, right? We have the glomerulus, right, followed by the efferent arteriole, and then we have the peritubular capillaries. So many body systems have the portal system. The liver also has a portal system. But what does it do, right? What does a portal system do in the context of what we're talking about? It basically allows you to deliver hormones very quickly from one spot to another, as you will see on the next slide. Before we get to that, though, let's talk about the kind of controlling hormones released by the hypothalamus. The hypothalamus controls the anterior pituitary gland using two groups of hormones. Okay, here we have a group of hormones called releasing hormone. You can think of this as like green lights. Okay, this is the go-ahead, the permission from the hypothalamus that tells the anterior pituitary gland to release some hormone. We already learned this in the reproductive system previously, right? We learned about GnRH, right, which is a releasing hormone that allows the anterior pituitary gland to release FSH or LH. Okay, you don't always want to allow the anterior pituitary gland to release something. In certain instances, you want to tell the AP, the anterior pituitary gland, to not release the hormone. In that case, the hypothalamus is going to release this thing called inhibiting hormone. So in a sense, the releasing hormone and the inhibiting hormone, they are working against each other, and then they are always going to be competing the effects onto the AP, and whichever one you have more, that's going to either let the AP release a hormone or stop releasing a hormone. In this picture, it goes through the steps of how the hypothalamus exerts its control on the anterior pituitary gland. So let's just go through it one more time quickly, right? You can see these neurons now ends at the stalk region, and you can also see at the stalk region, surrounding the stalk region, there is a network of capillaries, right? Over here, right? So these capillaries are connected to another network of capillaries through some veins, and that creates your portal system. So in essence, what happens is the hypothalamus will release, say, GnRH. Let me use a different color for you. They will release GnRH. This GnRH will immediately go into the capillaries and travel down through the veins to the other network of capillaries here. And immediately, when it gets to the capillaries here, that GnRH will be exposed to your anterior pituitary gland. And that's when the pituitary will respond to the releasing hormone. And in turn, it will give off, say, FSH or LH. Okay? So by having a portal system, it ensures any hormones released from the hypothalamus will have an immediate effect on how the anterior pituitary gland is going to function. Now we're going to talk about the different hormones produced by the anterior pituitary gland. Okay, two of these hormones produced by the anterior pituitary gland, they do not affect other endocrine glands. All right, and for that reason, we call them non-tropic hormones. Okay. They don't affect another endocrine glands. So remember that earlier slides, slides 2, where there's a diagram with all the endocrine glands. So these hormones, these non-tropic hormones, do not affect any of those glands. Right? So the first gland, the first hormone that belongs to this category is what we call prolactin, PRL. All right. So prolactin begins production at about 5th month of pregnancy, and this is the hormone that allows the milk production in the breast. Okay, and it will also play a role in carbohydrates and fat metabolism, because you have to do things a little bit different now. You need to divert some of these energy, some of these resources into the milk produced by the mother. All right. So combining what you learned in the previous slides, prolactin, PRL, basically mix the milk, and then oxytocin, which is from the PP, right? This is from the AP, right? So prolactin mix the milk, and oxytocin allows the milk to come out. So if I ask you on the test, what are the two hormones that are important for nursing a baby, make sure you know it's prolactin and oxytocin. Another non-tropic hormone created by the anterior pituitary gland is growth hormone. This is perhaps the easiest hormone that you will learn. By looking at the name, growth hormone basically is going to allow you to grow. So it will target things like cartilage, bones, muscles, and then all these things will respond to growth hormone. They will get longer, they will get bigger, which is what you need if you are hitting puberty, for example. Now, there are two conditions where there might be too little growth hormone produced during childhood, and as a result, you get what's called pituitary dwarfism. All right, and on the other hand, if there are too much growth hormone, then you get what's called pituitary gigantism. So you basically become very, very, very tall. People with pituitary gigantism, they have shorter life expectancy, because the heart muscle is usually not going to be able to accommodate or withstand the bigger size of the body, and so you would die prematurely. All right. So growth hormone and prolactin, they are both created by the anterior pituitary gland, and they are non-tropic hormones because they don't target another endocrine gland. And obviously, the release of both PRL and growth hormone would require some kind of permission from the hypothalamus, some kind of releasing hormone, right? But we're not going to talk about that in this course. The other four hormones that are produced by the anterior pituitary gland are called tropic hormones because they have an effect on other endocrine glands, and they are all listed here: TSH, ACTH, FSH, and LH. Although you can use acronyms on the final test for the written portion, I do recommend learning the full names, because knowing what the short form stands for actually tells you a little bit about what the hormone does. So we learned about follicle stimulating hormone, which is a hormone that will trigger the development of the follicle, right? So the name usually tells you quite a bit about what the hormone does, right? So in the following slides, we will be learning about the regulation of these hormones, and they actually follow some kind of theme. So very briefly, let's talk about the theme that we are going to see throughout the lecture, right? This theme has to do with a concept called the hypothalamic anterior pituitary axis. Okay, and you can see hormones that belongs to a particular axis is going to be responsible for regulating a particular homeostasis in the body. So let's begin with one that we know from the reproductive system. So we have the hypothalamus. Okay, we have the hypothalamus, and the hypothalamus is going to release a hormone, and that hormone is a releasing hormone usually. Okay, and that releasing hormone will then act on another structure, right? The anterior pituitary gland. And in response to that GnRH, the anterior pituitary gland will release, let's say, FSH or LH. And from there, the FSH and LH is going to travel through the bloodstream, and it's going to act on another target. And in this case, the target would be the gonads. And let's say we look at the male, so this would be the testis. And in response to the FSH and LH, it will release testosterone, right? And the testosterone is going to promote spermatogenesis, which I'm not going to put down here. And if you remember, the testosterone actually will travel back to the anterior pituitary gland and the hypothalamus, and it will exert a negative feedback so that you don't produce excess amount of testosterone. So it kind of regulates back onto itself. So this theme will be reoccurring for two other set of axes, and I'm just going to write down for you now, and we'll talk more about it as we go on. The next one, the next axis. But before the next one, this first one that we did, right? You can say it's responsible for regulating the reproductive system. Okay, reproductive system. The next one that we're gonna learn is pretty much the same thing. All right, you begin with the hypothalamus, right? Hypothalamus. And the hypothalamus will secrete some kind of hormone that acts on the AP, which would then secrete some kind of hormone, which would then act on some other target gland, and from that target gland, you're going to get some kind of hormone. So this second pathway that we're going to talk about regulates metabolism. Okay, metabolism. All right, so from the hypothalamus, you are going to have a hormone that comes out, and it's called TRH, right? Thyroid releasing hormone. You already learned, or you should know by now, that releasing hormone is the permission for the anterior pituitary gland to release something. So in this case, the TRH is the permission for the AP to release a hormone called TSH, thyroid stimulating hormone, right? And as the name implies, thyroid stimulating hormone is going to travel through your bloodstream, and it's going to go ahead and stimulate your thyroid, right? So you see, previously the final target gland was testicles, and now the final target gland, if you would be the thyroid gland. And the thyroid gland, in response to TSH, is going to release its own hormone. It's called T3 and T4, and I'll tell you what they do in a bit. And the T3, T4 will go back and negatively suppress these earlier hormones. Sorry, this should be right here. Okay. So this feedback theme is consistent. And just very briefly, you have a third pathway for stress. Okay, for short-term stress, long-term stress rather. We have CRH, which we'll talk about what it is later, and CRH is from the hypothalamus, which would then tell the AP to release something called ACTH, and then it's gonna cause the adrenal gland this time, right? Adrenal gland, right? Specifically the adrenal cortex to release something called cortisol. Okay, and cortisol will go back, and we will have the negative feedback. All right, so there are three main axes here, and you need to know them pretty well. But they all follow the same theme. Okay, they all started with some kind of releasing hormone from the hypothalamus, and then that will cause the AP to release some other hormone, which would then target some final gland, and finally from that last gland you will release some other hormone. All right, so it might not make much sense now, the hormones themselves, but you should see that the theme is the same. Okay, that's why it's called the hypothalamic anterior pituitary axis, because it always include the hypothalamus at the top, then the anterior pituitary, and they belong to the same path that regulates something. Okay. So let's talk more about the thyroid gland and the parathyroid gland. Just to refresh your memory, your thyroid gland is kind of where your larynx is, and your parathyroid gland is actually behind it. So you can't really see it here, okay? But like I can draw a little yellow dots here. Like if you were to look at it from the side, you might be able to see your parathyroid gland. There are actually 4 parathyroid glands. I guess I can draw the thyroid gland again, and then let's say you're looking at it from the back, then you would see the parathyroid glands are there. Okay, so there are 3 hormones that we will learn, 3 hormones that are released from the thyroid gland, and there is one hormone that is released from the parathyroid gland. Before we talk about new stuff, let's talk about things you've learned from this course already. One of the thyroid hormone is called calcitonin. You might remember calcitonin is a hormone that is responsible for maintaining blood calcium level. All right. In case you forgot, calcitonin is released when there is too much calcium in the blood, right? Then it will cause calcitonin to be released, which would then bring the calcium level back down. All right. So that's calcitonin. And one way to bring the extra calcium back down is by depositing the calcium into the bones, right? So actually having sufficient amount of calcium in your diet when you are growing up is important, because it would allow calcitonin to take all those extra calcium and deposit them into the bones, so that your kids or you will actually be able to grow. All right. So that's calcitonin, one of the 3 hormones from the thyroid gland. The other 2 hormones are T3 and T4, right? They stand for these long names, but you don't have to worry about it. You can just say T3 and T4. Their functions are pretty redundant. They're overlapping each other, so there's no distinction for our purpose, right? And T3 and T4, they are the only thing in the entire body that uses iodine, okay? And we will talk about what happens when you don't have enough iodine in your diet. So T3, T4 in general is responsible for increasing metabolic rate. Basically, the more T3, T4 you have in your bloodstream, the higher your metabolism is going to be, right? So faster metabolism includes breaking down glucose quicker. It means you will get warm as a result of these metabolism, right? But your metabolism is not going to increase forever, because as you saw in the previous slide, right, when you have an increase in T3, T4, right? This is the end of that axis. These T3, T4 will actually go back to your anterior pituitary gland and your hypothalamus and inhibit its own secretion, right? So these kind of regulation are called negative feedbacks. Here is the axis I have been talking about again, right? We started at the hypothalamus, and usually what stimulates the hypothalamus in the context of metabolism is a low level of thyroid hormone. Okay, so if you have low T3, T4, it means your metabolism is low, which means you need to create hormones that will turn it back up, right? Think of this as the thermostat, right? When do you want to turn on the heat? You want to turn on the heat when the house is cold, right? So you want to turn on the production of T3, T4 when it is low, okay? So low T3, T4, low metabolism, that will serve as a stimulation for the hypothalamus to produce TRH, right? Thyroid releasing hormone, right? Which is nothing more than a permission for the anterior pituitary gland to release TSH, the thyroid stimulating hormone, right? And that TSH is going to go travel to your thyroid gland, which is right here, in response to that, the thyroid gland is going to release thyroid hormone, specifically T3 and T4, right? And T3, T4 will then turn the metabolic rate higher. But at the same time, these rising level of T3, T4 will inhibit the secretion of TRH and TSH. It's all about control, right? Go back to the thermos idea. Once the furnace turns on, once the house starts to get warmer, you want to turn the furnace off. You don't want it to keep on increasing the temperature, right? You just need to maintain a particular balance, particular set point. And that's why negative feedback loops are so important. So there are two ways that things can go wrong in terms of thyroid hormones. Okay, we will talk about hyperthyroidism first. Okay, there are different ways to get hyperthyroidism, but one of the most common examples is what we call Graves' disease. In Graves' disease, your body creates an antibody, an autoreactive antibodies that will be stuck to your thyroid gland. So let's think about the consequences of that. So here is your thyroid gland, okay, and the thyroid gland, if you have antibodies stuck to it, remember, normal people don't have these antibodies. Only people with Graves' disease would have these antibodies. These antibodies would get stuck to the thyroid gland, and it will basically turn it on all the time. Under the stimulations of the antibodies, the thyroid gland will release a lot of T3 and T4, right? So these T3, T4 will cause your metabolism to increase. Let's think about what the T3, T4 will do to the hypothalamus and the thyroid gland. And the anterior pituitary gland. So these T3, T4s will actually go back to your hypothalamus, and it will suppress it with a negative feedback control. And so in the presence of these high T3, T4, your hypothalamus will actually decrease the TRH secretion, right? And at the same time, some of these T3, T4 will go to the anterior pituitary gland, and it will decrease the level of TSH, okay? Now, if this was a normal individual, the decrease in TSH should then tell the thyroid gland to slow down on the production of T3, T4. But that's not the case for hyperthyroidism. Despite the fact that you have low TSH, the thyroid doesn't care. The thyroid will continue to pump out a lot of T3, T4 because it got these antibodies stuck on it. So this is like having a furnace that doesn't respond to your thermostat. You try to turn the thermostat down, but somehow is not communicating with the furnace. The furnace is always on, and so it just keeps on producing T3, T4, and the metabolism is just going to keep on increasing and increasing. All right, so that's hyperthyroidism. And on a side note, for people who get their thyroid being stimulated consistently this way, they will get goiter, right? Goiter is the enlargement of the thyroid gland because it's being stimulated so much. So if you do a blood test on someone with hyperthyroidism, you are probably going to find low TRH, low TSH, and high T3, T4, resulting in high metabolism. Bottom line, the thyroid gland will continue to produce large amount of T3, T4 despite the fact that you have low TRH and low TSH. This slide just basically summarizes what I've already said in the previous slide, and that's what goiters looks like if you've never seen a picture of that before. Now, interestingly, one other characteristic of someone having Graves' disease are the eyes protruding a little bit. It's called exophthalmos. And the reason for that is because the antibodies that you produce, the autoreactive antibodies, they will also target the muscles located around the eyes, causing them to become inflamed. And it is the inflammation of these muscles that gives the appearance of protruding eyes. Due to the high metabolism, some of the symptoms that someone with hyperthyroidism will feel include a high body temperature, right? They will feel too hot all the time. They might have fast-growing and rougher fingernails, again, due to the increased metabolism. And sometimes you might have increased muscle degradation as a result of that, causing you to have weaker muscle. And because you're burning your fuel so quickly, you might feel hungry all the time, and you will eat more, but your body will continue to lose fat and weight because you are basically burning everything you eat. Rapid heart rate, hand trauma, perspiration, irritability, all these are examples of hyperthyroidism. One treatment for it is to use radioactive iodine. Basically, iodine, if you take it, will only end up in your thyroid. That's the only place that your body uses it. And if you give the person radioactive iodine, then basically these radiation is going to suppress the activity of the thyroid gland. The opposite of hyperthyroidism is, of course, hypothyroidism. There are many ways to get hypothyroidism, and again, I'm just going to explain the most simple concept, which is iodine deficiency. So if you don't have enough iodine in your diet, then what happens is your thyroid gland now does not have the raw material to make T3, T4. So what comes out of it is very little, right? T3, T4. And because you have very little T3, T4, your metabolism is going to be low, okay? Then what happens? Well, with a drop in T3, T4, right, you might remember from a couple slides before, that will tell the hypothalamus, right, that will act as a stimulation for the hypothalamus to make more TRH, which then would tell the anterior pituitary gland to make more TSH. This increase in TSH will now stimulate the thyroid, okay? But the thyroid cannot do anything about it because there isn't enough iodine. So you can stimulate the thyroid all you want, but the T3, T4 level will not increase any further until you have iodine available in the body. And so this continuous stimulation of the thyroid gland will cause it to become big. So again, you will get goiter, okay? But the T3, T4 level will continue to be low. So if you do a blood test on someone with hypothyroidism, you are likely to find high levels of TRH, high levels of TSH, but low levels of T3, T4. On a side note, just because someone has goiter, someone has an enlargement in the thyroid gland, just by looking at them, you actually don't know necessarily if they have hyper or hypothyroidism. you don't actually have to worry about iodine deficiency in Canada or North America for that matter, because our table salts are actually mixed with iodine in it to prevent the exact same situation, to prevent iodine deficiency, right? So if you eat any kind of products containing salt, you basically would have adequate amount of iodine intake. So this slide shows you other forms of hypothyroidism depending on whether you get it later in life or early in infancy or childhood. I won't be testing you on these things. You can just read through it for interest's sake. So the parathyroid gland is once again located behind the thyroid gland. And you can think of them as four small knobs that are kind of piggybacking on the thyroid gland. Okay, and the parathyroid gland secretes the parathyroid hormone (PTH). PTH is antagonistic to calcitonin. All right, when you have a decrease in blood calcium level, that's when you will release the PTH. All right, and the PTH will help you bring the blood level calcium back up by promoting reabsorption of calcium in the kidneys, activation of vitamin D, which will help you absorb calcium from the intestines. It will also break down a little bit of your bone, stimulating those osteoclasts, which would dissolve the calcium from the bones and make them available in the bloodstream. All right, so just a side note, right? If you take calcium supplement, you should probably take ones that comes with vitamin D's, right? Because without the vitamin D, it's difficult for your body to absorb the calcium. So we have talked about two of the axes already, and now we will shift our focus to the adrenal gland, and this one is the one that involves the stress management, right? We have the CRH, the ACTH, and something called cortisol. So we will get to this eventually, but let's take a look at a few other things first. The adrenal gland. The adrenal gland sits on top of your kidneys. Okay, it's like your kidneys is wearing a hat or something, and those adrenal glands are separated into the adrenal medulla, right, which is the inner portion of the organ, and the adrenal cortex, which is the outer portion of the organ. In general, you can think of the adrenal medulla is responsible for responding to immediate stress, like an angry dog running towards you. That's immediate stress, and it is the adrenal medulla that is responsible for responding to that. Whereas the adrenal cortex is more for long-term stress. Okay, long-term stress, such as being in school, right? Losing a job, right? Losing someone you love, right? All these are going to create long-term emotional and physical stress, and that's going to cause the adrenal cortex to secrete certain hormones, right? We'll go into more details of these later, but right now it's important to know that the adrenal medulla, the one responsible for immediate stress, is under nervous control, right? In fact, it's under the sympathetic pathways, if you remember it from the nervous system, whereas the adrenal cortex is more under hormonal control, specifically ACTH. So as I said, the hormone produced by adrenal cortex provides long-term response to stress. It is energy demanding for your body to remain in a stressful state, and so the main goal of these hormones in a long-term stressful situation is to increase resource availability for your body. So there are two types of hormones produced by the adrenal cortex. One is belonging to the category of mineralocorticoids, and the other the glucocorticoids. Mineralocorticoids are responsible for regulating salt and water balance, and you want to increase your blood volume, increase your electrolyte balance, as part of your resources. And one of the most important mineralocorticoid is the aldosterone, which you've learned in previous lessons, right? Aldosterone is responsible for absorbing sodium chloride, which ultimately lead to increase in blood pressure. So for people who are chronically stressed, right, it's not surprising that their blood pressure might be a little bit higher than usual, and part of the reason is because of this aldosterone. The other hormone secreted by the adrenal cortex is what we call glucocorticoids. Okay, glucocorticoids is again a group of hormones that will help you regulate basically macromolecules, including carbohydrates, proteins, and fat, and how you metabolize them, right? And you will metabolize these proteins and fat in hope to increase the blood sugar level. As I said, it's energy demanding to remain stressful, right? And so you need to have all these extra resources. The most important glucocorticoids in the body is what we call cortisol. Okay, so you might have heard of cortisone before, right? Or like hydrocortisone. That is actually the medical equivalents of cortisol, right? That's basically a drug that is very similar to this, and you can use it for suppressing inflammation, right? In fact, a lot of the acne creams out there contains the hydrocortisone, right? Perhaps at lower levels, and it could subside inflammation, and you will see why in a second. So the main goal of cortisol is to increase blood glucose level, and it can do it in at least two ways. Okay, it can promote the breakdown of muscle proteins into amino acids, and as you learned previously, amino acids can then be taken up by the liver, where they will be converted into glucose, right? And then the glucose go back to the blood, and you can use it for cellular respiration, for example. Cortisol is also going to metabolize fatty acids in your adipose tissue rather than carbohydrates, because the same amount of fat versus sugar, the fats can actually generate a lot more energy. But in addition to that, you want to save the good stuff, right? The glucose for the brain, right? And the rest of the body can kind of run on this energy reserve, right? This fatty acids, right? And you will spare the glucose again for what importance the most, right? The brain. Although I have been saying cortisol is responsible for increasing resource availability for long-term stress, but it turns out the cortisol level in your bloodstream under normal circumstances will actually fluctuate a little bit up and down throughout the day. And in fact, your cortisol level is going to be usually a little bit higher in the morning. And here is why, okay? When you're sleeping, for example, you are not necessarily eating, and so you might not have enough resources in the body, right, to run things properly, so to speak, right? And so it's not uncommon that the cortisol level will be a little bit higher in the morning when you wake up. And these cortisols will allow you to promote cellular uptake of glucose from the blood, right? It might even break down a little bit of proteins or fat as energy resources. But here's the thing, when you are otherwise not stressed out, the cortisol will go back to the anterior pituitary gland and the hypothalamus in a negative feedback to shut off its own production. So if you're not stressed out, if you're just like going through your days normally, then your cortisol level is not going to be too high. It will fluctuate a little bit, right? But it will never be too high. So if I represent this on a graph, for example, right, then your cortisol level might just be like going up and down, day in, day out, okay? Because it's able to regulate itself. All right. So before we go more into this graph, let's go back to the axis, right? So your blood level of cortisol is low. That will tell the hypothalamus to release the CRH, right? And the CRH will stimulate the anterior pituitary gland to release ACTH, which would cause the adrenal cortex, right, to produce cortisol. But then cortisol is going to negatively inhibit itself. And here is the thing. if you suffer from long-term stress, right? If you say lost a job or something and you feel stressed about it, then your central nervous system, your CNS, will actually override these negative feedback controls. Okay, so the central nervous system will prevent the cortisols from self-regulating, and in that context, the cortisol level will continue to rise until it reaches some kind of new normal. All right, so this here, right, is what I was talking about, the long-term stress, right? Then things are really going to change, physiologically speaking. You are going to continuously promote protein breakdown and fat breakdown, and cause your blood sugar level to be high, right? And all that in effort to maintain a long-term stressful situation. So unless that stressful factor is gone, the cortisol level will remain high. So this is just words of what I've said on previous slide, right? Normally speaking, cortisol secretion is controlled by negative feedback to AP and hypothalamus. And I just want to say, this is the same thing we have been talking about. For example, T3, T4 secretion is governed by negative feedback loop to the anterior pituitary gland and hypothalamus, right? Okay, testosterone secretion is governed by the same negative feedback, right? So it's a theme about the axes that we have been trying to develop, all right? So let's go back to cortisol, okay? Cortisol is normally going to regulate itself, but in times of stress, long-term stress, the central nervous system is going to override the feedback control, and so cortisol level will keep on going up, right? Excess cortisol is actually bad for your health, right? Physiologically speaking, that chronic stress will interfere with growth, with immune system. Of course it will, because you're taking precious resources such as proteins, which is needed for growth, which is needed for, say, producing antibodies for your immune system. All that resources are going to be diverted for glucose production, and so your growth is going to be interfered, your immune system will go down, sexual function, cardiovascular functions will also be affected. Let's go back to that acne cream I was talking about. Because of the effects of cortisol, right, its suppression on the immune system, that's why these cortisone that you found in the creams are anti-inflammatory, right? Because it suppresses part of your immune system. Finally, chronically high cortisol levels can actually harm cells in the hippocampus. And of course, you remember the hippocampus is where you will learn things and remember things, right? Formation of new long-term memories. So by being stressed out, you actually don't remember things as easily. So everything we talked about for cortisol was part of the adrenal cortex, okay? But when you are in an immediate dangerous situation, it is the adrenal medulla that will give you the physiological response that you have experienced. So the adrenal medulla secretes two major hormones, epinephrine and norepinephrine. Okay? Epinephrine and adrenaline is actually the same thing, right? Two different words for same thing. And norepinephrine is actually the same thing as noradrenaline. Both of them are produced by cells in the adrenal medulla, and it will create what we call the fight or flight response, right? We learned this previously in the sympathetic pathways, right? You will experience increase in heart rate, rapid respiration, dilation of pupil, so on and so forth, okay? All these are brought on about from the hormones epinephrine and norepinephrine in response to immediate threat, okay, short-term stress. But as you know, right, if you are excited about something, the same kind of effect is going to take place. So this slide summarizes the hypothalamus exerting effects on the medulla as well as the cortex of the adrenal gland. The control for the adrenal medulla is a nervous control. Okay, it's when you see something dangerous happening to you, right? Again, like an angry dog running towards you or something, the hypothalamus is going to send an action potential down the spinal cord, and then it's going to exit through these sympathetic pathways, which would then cause the adrenal medulla to release the stress hormone, the epinephrine and the norepinephrine. This is an action potential, which means it is an electrical signal, so it happens almost immediately, which is perfect if you're trying to respond to short-term stress. Long-term stress is different. Long-term stress doesn't happen overnight, okay? It takes some time before your body reaches that state, and that's because it's a hormonal regulation. So hypothalamus will release the CRH. CRH will cause the AP to release ACTH, and ACTH will tell the adrenal cortex to release glucocorticoids, right? Which include things like cortisols, and mineralocorticoids, which includes things like aldosterone, right? So normally these things will go back and negatively inhibit itself, but again, in long-term stressful situation, your central nervous system will block these inhibiting pathways, and so cortisol level will continue to rise. But the key thing is it doesn't happen overnight. It takes some time for your central nervous system to override the negative feedback loop, right? And so long-term stress happens gradually, right? Some people don't even realize they are long-term stressed out until much later. Continuing on to the rest of the endocrine glands, we now have the pancreas. Okay, so pancreas secretes several hormones that helps you regulate glucose level. Pancreas is kind of unique in the sense that it is both an exocrine and an endocrine gland. Right? If you remember, exocrine glands or exocrine tissues, they make their secretion through some kind of duct. Okay, so the pancreas is an exocrine gland because when it secretes digestive juices, right, the pancreatic juice, it actually goes to the duodenum through the pancreatic duct. Okay, so other example of exocrine glands, just for reference, include things like a salivary gland, right? Includes things like sweat gland. They all secrete through some kind of duct. An endocrine gland is different because endocrine gland is going to secrete their contents directly into the bloodstream. All right, and pancreas can certainly do that. There are three types of cells in the pancreas. We have the alpha cells, which produce a hormone called glucagon. We have the beta cells, which produce a hormone called insulin. Okay? And these cells are grouped in clusters that are referred to as the pancreatic islet or the islet of Langerhans. Finally, there is this third type called delta cells, which produce somatostatin, but we won't be focusing on that. We will just talk about the glucagon and the insulin. This slide just shows you where the pancreas is located in case you've forgotten, but you should remember from the digestive system. So insulin. Right? Insulin is not necessary for the brain to uptake glucose. Right? In fact, red cells also don't need insulin to take up glucose. They just kind of do on their own. Okay, it makes sense. I mean, you want your brain cells to be pretty alive all the time, so they would be able to take as much glucose as they need just by themselves. But when we talk about muscle cells and fat tissues, they cannot actually absorb glucose from the blood unless there is insulin. Okay, in the liver, in the muscle, the insulin is actually going to help trigger the conversion of glucose into the storage form, glycogen. Right? So when you have a meal and you eat more than you need, all right, then the insulin will promote the liver and the muscle cell to take up those extra glucose. They will use what they want and what they need, and the rest of it are going to be converted into the storage form, the glycogen. And obviously the glucose will allow the muscle to contract and be able to move, right? And finally, the insulin is going to promote the conversion of glucose into fat in your fat tissue, in your adipose tissue. So together, collectively, these things would bring your insulin level back down. Right? So when would you expect to have insulin in the body? Usually after a meal. Okay, after you eat something, your glucose level will be high in the bloodstream, and the insulin will do all these things to bring it back down. Right? Your regular blood glucose level should be around 0.1% concentration. The antagonistic hormone of insulin is glucagon. Right? This one also comes from the pancreas, the alpha cells of the pancreas. There's an A in glucagon, so that helps you remember it is the alpha cells that makes it, right? And the beta cell makes the insulin. So the glucagon is going to be secreted when your blood glucose level is low. So in between meals, right? Or if you skip a meal, then glucagon level will be high. And the purpose of glucagon is to increase the sugar level in your blood. So it targets liver and it targets adipose tissue, and it basically reverses what insulin did. Okay, so you store some glucose as glycogen when you had insulin in the body, and now the glucagon is going to tell the liver to break down the glycogen back into the glucose, and so you can use it, right, for energy sources, right? And the adipose tissue is going to break down fat into glycerol and fatty acid, and you can use them for glucose formation, right? And we learned this previously in the digestive system. It's called neoglucogenesis, right? So together, insulin and glucagon, they are going to help you maintain blood. This is a good summary of how insulin and glucagon work against each other to maintain homeostasis for blood glucose level. This is taken from your textbook, so please go find the page and review it accordingly. So let's quickly talk about diabetes, right? Diabetes is a fairly common hormonal disease where it has to do with insulin sensitive cells in the body not able to take up the glucose, right? So the bottom line is for diabetes that the glucose in the blood remains high, all right, because your body is not absorbing it, right? It's in the blood, but it's not able to get into the cells, right? Sure, it will get into your brain cells and your red blood cells, but it will not be taken up by the muscle or by the adipose tissue. So it remains high in the blood, creating a situation called hyperglycemia. Okay, anything that ends with emia means it has to do with the blood, and in this case, it is too much glucose in the blood. Because the body cells are not being able to access the glucose, so your body thinks you are starving. Right? So your body goes into starvation mode. And a couple of things could happen when you switch into starvation mode. We'll talk about that on the coming slides. And as the blood sugar level rises, right, you learn in the urinary system, right, all these extra glucose will be filtered at the glomerulus, and you won't be able to absorb all of it back at the proximal tubule, and so they all come out in the urine, creating glycosuria, right, which basically means glucose in the urine. And with the extra glucose in the urine, it actually will increase the osmolarity in your filtrate, causing more fluid to be retained in your nephrons, and so you will have high volumes of urine, right, and you will be urinating quite frequently, and we call that polyuria. So for these reasons, loss of water, the diabetic patients are usually quite thirsty. So once again, the glucose in the blood are not being taken up by your cells, and so they think you are starving, and the body is going to turn to other resources to create energy, such as protein and fat. And when you metabolize fat, without going into too much detail, it actually elevates the amount of ketones in the blood. And you probably learn about ketone in your organic chemistry. And these ketones is actually a little bit acidic in nature, which could cause your blood pH to drop significantly and creating a condition called acidosis. So acidosis can lead to coma or death, which means diabetes, if you don't treat it properly, it could be life-threatening. Generally speaking, we have type 1 diabetes and type 2 diabetes, and there is also one that you can get when you're pregnant. We call it gestational diabetes. Let's talk about type 1 diabetes. Type 1 diabetes, or sometimes called juvenile diabetes, which is quite a bad name because not only kids get it, grown-ups can get this type of diabetes as well. Type 1 diabetes is a situation that occurs when your white cells attack the insulin-producing cells in the pancreas. So basically, it's an autoimmune disease where your immune system destroys the beta cells in the pancreas, and so you're not able to make insulin. Without insulin, then again, all the glucose stays in the blood and you will experience all the symptoms that we've talked about. So for that reason, people with type 1 diabetes, usually their blood insulin level is low, and the way to treat that would be to give them insulin shots, right? You have to be careful. Well, when this was first studied, right, and people will have to give themselves insulin shots is dangerous if you inject too much, right? Because then all the sugar will be taken up by your cells, and then not enough will go to the brain, and so you might faint as a result of hypoglycemia, too little glucose in the blood. But nowadays, people don't usually have that problem. There are machines that you can wear, and they will monitor the fluctuation in your blood glucose level, and it will deliver the injection when necessary. In fact, I've seen this new thing with a little implant underneath your skin, and it will communicate with your smartphone, and you will be able to get a real-time readings on your blood sugar level. Now, type 2 diabetes is a little bit different. It is not autoimmune disorder. It has to do with more like a lifestyle thing. In type 2 diabetes, the insulin levels are usually normal or even quite high. It has to do with insulin resistance. Okay, so basically, due to poor diet, for example, and low levels of physical activity, your cells do not respond to insulin the same way or with the same intensity as it used to, right? And gradually, your body is going to have to make more and more insulin in order to stimulate the cells to take up the glucose. But there is going to be a point where your cells will completely kind of ignore the signals from the insulin and not respond to it at all. And so for these people, giving them insulin shot is not going to help. I mean, they have insulin. It's just that their cells are not responding to it. The main treatments for type 2 diabetes, which is a very common disease in North America, is to change the diet, right? Exercise, right? And most oral medication aims to bring glucose level back down, right? So there is a common drug called metformin used for type 2 diabetes. And it inhibits the conversion of glycogen into glucose at the liver, right? So that's going to help bring the glucose level in the blood back down. So the hardest stuff is over, right? We just have a couple more slides to go through about the gonads, which you've learned excessively in the reproductive system already, so not much on that. Just a few words on the pineal gland and the thymus, and we will be done. Okay, so for the gonads, right, make sure you know about the GnRH, the FSH, LH, right, testosterone, estrogen, progesterone, and their effects on the menstrual cycle, for example, and on spermatogenesis. Basically review what was taught in the previous lesson, right? Also watch that video I create for the menstrual cycle. It will help you understand the interaction of various hormones. The pineal gland, right? The pineal gland is located deep in the brain and somewhat posterior. And the hormone that comes out from the pineal gland is melatonin, right? Melatonin is primarily released at night because the trigger for melatonin is actually low light, right? And it involves in your sleep-wake cycle or what we call like a 24-hour cycle, the circadian rhythms, right? Your biological clocks. So by having melatonin in your body, you will feel sleepy, right? And that basically helps you go to sleep, which is why they say, right, don't watch too much TV or look at your cell phone too much before you sleep, because that light is actually going to lower the melatonin level in your bloodstream, and so it will make it more difficult to go to sleep afterwards. People buy melatonins from nutrient supplement stores, right? And they say it's going to help them go to sleep. But some studies suggest that it's just a placebo. Somehow taking the melatonin is a little bit different than making your own naturally. So pineal gland secretes melatonin. Melatonin makes you sleep. That's basically what you need to know. And thymus. We have not talked about the thymus since the immune system, right? Your thymus is close to the heart, right? Please do not confuse thyroid with thymus. Your thymus secretes one hormone called thymosin, and thymosin is responsible for the maturation of lymphocytes, particularly the T cells that we've learned about. And that's all you have to know, okay? Thymus releases thymosin, which helps T cells mature. So that's it. That's all the hormones that you have to know for the endocrine system. I'm going to be creating a separate video that I'll post on YouTube that helps you summarize all these using your course pack. So make sure you go take a look at that as well. Okay, thanks for watching.